All right, today we are tackling one of the biggest, most important ideas in all of physics, but it's also, maybe, the most misunderstood. This is a concept that governs literally everything, from how molecules jiggle to how massive storms form. It might even be the very reason time itself seems to flow forward, and maybe even why we're here at all. And to really get it, we're going to start with a question that sounds, well, almost too simple.
So what does planet Earth actually get from the sun? Now, your first thought is probably energy, right? Or maybe heat or light. And look, you're not wrong, but that's not the whole story, not even close. In fact, it kind of misses the most incredible part. You see, if you look at our planet's energy budget, it's pretty much balanced. For the Earth's temperature to stay more or less stable over time, the energy we absorb from the sun has to be about equal to the energy we radiate back out into space. If it wasn't, well, the planet would just get hotter and hotter and hotter, or colder and colder. And that right there is a fantastic puzzle. If the energy account breaks even every day, if what comes in is what goes out, then what on earth are we actually getting from the sun? What's the secret ingredient that powers all of the complexity, all of the weather, all of the life on our planet? Well, to find the answer, we have to jump in a time machine and go back about 200 years. Believe it or not, our journey takes us right into the heart of the Industrial Revolution. The answer to our cosmic question is hiding in the steam, soot, and steel of the quest to build bigger, better, and more powerful engines. So let's meet our main character, Sadi Carnot. He was a brilliant young French physicist and military engineer, and back in the early 1800s, he was seriously worried. He saw Britain's industrial power growing, and he knew a big part of it was their steam engines. France's engines were, well, they just weren't very good. So he made it his mission to figure out the absolute fundamental rules of how you turn heat into work.
And, they were really inefficient. We're talking the very best steam engines of the day were only managing to convert about 3% of the heat energy from burning coal into actual useful work. 3%! The other 97% was just gone, wasted. So Carnot asked, what's the limit? What's the absolute best we could ever do? Could we ever build 100% efficient engine? To figure this out, Carnot dreamed up a perfect, idealized engine. No friction, no leaks, nothing. It works in 4 simple steps. First, you add heat. A gas expands and it pushes a piston up. Great, that's work. Then, the gas keeps expanding on its own, and as it does, it cools down. Now, and this is the absolute key to the whole thing, to get the piston back to the start so you can do it all over again, you have to compress that gas. And in doing so, you have to dump some of that energy as waste heat somewhere cold. The last stroke just brings it back up to the starting temperature, ready to go again.
And that is the mind-blowing insight. In order to make an engine that can run in a cycle over and over again, you have to throw some heat away. You just have to. It's not a choice. This means you can never, ever convert all the heat into useful work. A 100% efficient engine isn't just hard to build, it's physically impossible. It's a fundamental law of the universe. So this unavoidable tax, this mandatory loss of useful energy, it needed a name. It took a few decades, but another physicist, Rudolf Clausius, came along, formalized the idea, and gave it a name that has been confusing physics students ever since. He called it entropy. Now, I want you to forget whatever you heard in high school about disorder or messiness. The best, clearest way to think about entropy is just as a measure of how spread out energy is. That's it. Concentrated, useful energy, like the heat in a chunk of burning coal, has low entropy. Spread out, less useful energy, like the faint warmth of the air in a room, has high entropy. And this simple idea led Clausius to write down one of the most powerful and profound statements in all of science. It's the Second Law of Thermodynamics, and he put it like this: the entropy of the universe tends to a maximum. What does that mean? It means left to its own devices, energy always spreads out. It flows from hot to cold. It disperses. It never, ever spontaneously clumps back together. So think about this. The total amount of energy in the universe never changes. That's the first law. But the quality or the usefulness of that energy is always going down. Every single thing that happens, from a car engine running to you digesting your lunch, takes some nice concentrated, low-entropy energy and spreads it out, increasing the total entropy of the universe. It's an irreversible process that leaves less useful energy behind than you started with. Okay, but that just brings up an even deeper question, doesn't it? Why? Why does energy only flow one way? Why do we see an egg scramble, but we never, ever see it unscramble itself? Why does time feel like a one-way street? The answer, as it turns out, is all about playing the odds. So for this, we have to thank another giant of physics, Ludwig Boltzmann. What Boltzmann realized is that a cup of coffee getting hotter on its own isn't technically impossible by the laws of physics. It's just so mind-bogglingly, ridiculously improbable that you would have to wait trillions upon trillions of times the age of the universe to ever see it happen. It's purely a numbers game.
Let me give you an analogy that makes this crystal clear. Think about a Rubik's Cube. Out of all the possible ways you can arrange its squares, there's only one single way for it to be perfectly solved. That is a very specific, highly ordered, low probability, low entropy state.
Now, how many ways can that same cube be a complete jumbled mess? Oh, just about 43 quintillion ways. That's a 43 with 18 zeros after it. So if you just close your eyes and start making random turns, which state are you almost guaranteed to end up in? A messy, jumbled, high probability, high entropy state. It's not magic, it's just statistics. And that right there is the arrow of time. The universe is just doing what the Rubik's Cube does. It is constantly moving from less likely, more ordered states toward more likely, less ordered states. That's why we remember the past, but not the future. The relentless, one-way flow of time is nothing more than the relentless increase of entropy. So, now that we have this incredibly powerful new way of seeing the universe, we can finally go all the way back to the beginning and solve our puzzle. What is the Earth really getting from the Sun? And here's the answer. We don't get a net amount of energy. We get a net quality of energy. The Sun isn't just giving us energy. It's giving us a constant fire hose of beautifully concentrated, highly ordered, incredibly useful, low-entropy energy. Let's look at this cosmic transaction. For every one high-energy, low-entropy photon of visible light that the Earth gets from the Sun, it turns around and radiates about 20 lower-energy, higher-entropy infrared photons back out into the cold void of space. So the energy budget is balanced, but the entropy budget is not. Earth is basically a giant entropy-exporting machine. And that is the secret of life. Life is this gorgeous, complex process that grabs onto this incoming stream of low-entropy sunlight. A plant uses it to build complex sugars. An animal eats the plant, and at every single step, that concentrated energy is used, processed, and radiated away as messy, high-entropy heat. Life doesn't fight the second law of thermodynamics. It is the most beautiful and complex way of fulfilling it. We are agents of entropy.
So you might hear all this and think entropy sounds kind of bad, like it's all about decay and disorder. But think about it this way. A state of really low entropy, like a cup of tea with a drop of milk sitting perfectly separate on top, it's actually pretty simple, kind of boring even.
It's in the messy middle. It's in the process of entropy increasing that all the magic happens. It's where the milk swirls into the tea, creating beautiful, intricate patterns. It's where stars ignite, where planets form, and where life itself emerges and thrives. All the complexity we see in the universe doesn't exist in spite of this law. It exists because of it. And that leaves us with one last, massive thought. Our universe started in this strange, remarkably low entropy state, and it's been getting more entropic ever since, creating galaxies and us along the way. But what happens when that process is finally done? What does the universe look like when entropy finally reaches its absolute maximum? A state that physicists chillingly call the heat death of the universe. Now that is something to think about.